Hello again, nerds. I hope everybody's feeling fantastic today. Get out of here, get out of here. Talking about the absolute value function today. The absolute value function is one of the, what pre-calculus calls 12 basic functions. Of course, this isn't pre-calculus, but when you go to pre-calc next year, you'll hear that terminology. Absolute value functions are shaped like V's, okay? They're V-shaped graphs, and they're either going to point up or they're going to point down. But because we can't remember if we've ever learned how to graph these things before, we're going to start from the basics. What does absolute value of a number even mean? A lot of students think it means, oh, just make it positive. Well, no, that's what it does to numbers, but that's not what it means. The absolute value of a number literally means how far away from zero is that number. And we make that distinction because when we get up into higher mathematics, we start dealing with numbers that are not on the x-axis, like the imaginary numbers. They're not on the x-axis, but we can still figure out how far from zero they are. But it doesn't make any sense to say what's the absolute value of a number when it has two dimensions, which is what an imaginary number is. We'll talk more about that maybe later in this year, but definitely next year. For now, I just want to make the distinction. Absolute value just means how far from zero is that? Of course, on the x-axis, that literally means if it's positive, it stays positive, and if it's negative, it's just positive. Because the number -5 is, well, it's 5 away from zero. And the number 7 is 7 away from zero. So yeah, its result is, if it's just regular old numbers, make it positive. If you didn't know how to graph something, you've never seen its picture before, and you were told, do your best to draw this graph, what would you do? Well, you would pick a whole bunch of x values and plug them all in and try to follow the order of operations, and you would get y values. Make a point tree, connect your dots. So I have to make sure that you guys have the ability to even do that. So these first 4 examples are literally just us taking numbers and plugging them in and getting results out. Remember what f of x stands for. It says y equals. Your y values are given to you by saying the absolute value of x minus 3. So when I say find f of -5, I'm actually saying what is the y value when x is -5? The reason why we would want to know is because we would then plot this as an x comma y coordinate. X's go in, y's come out. We have an x comma y pair that we could plot. Cool? Okay. So these first 4 examples are us just practicing plugging x values in. Excuse me while I throw my pen. Going to be replacing x with -5. And then what you have to do is follow the order of operations. Now this one's really simple. I'm aware there's not a whole lot going on. If you look here, you see there's a lot more going on. When we follow the order of operations, the first letter is P, parentheses. And it tells us if there's anything that can be done inside the parentheses to clean it up, do that. Your absolute value bars behave in the same way. Before we do any absolute values of anything, we try to simplify whatever's on the inside as much as possible, just like you would with parentheses. So I have absolute value of, and -5 minus 3 is just -8. At this point, because there's nothing but a value in these absolute value bars, we can let them do their job. And we can say, well, what is the absolute value of -8? And you guys would just say 8. Perfect. There we go. Not 7. I heard you. So if I was trying to plot this graph, this got me the coordinate. I'm just really trying to drive this idea home. This got me the coordinate -5, 8. I could put that on a grid with a whole bunch of other things and connect the dots. So even if I had no idea what this graph looked like, I could just get a whole bunch of x, y's and connect the dots in my best, with my best effort, right? Okay. Different function, different x. I'm changing colors because it's fun. What is this one? 6. All right. Before I finish this one up, I want to point something out. If these absolute value bars were parentheses, then you could distribute that -2. But these are not parentheses. The -2 cannot be distributed to the insides of these bars. Ever. Never. Okay? Treat them like the bars on a jail cell. X plus 1's not getting out, and -2's not getting in. -2's just visiting. They're talking through the glass. But these numbers don't play with these numbers. Okay? Just wanted to make sure that that was something that I discussed. Okay, now let's go ahead and finish this thing up. Well, 6 plus 1 is just 7. And when you say the absolute value of 7, it's just 7. It's just 7. So this one's even easier than the last one. We'd have to think about how far from 0 a number was, right? It's just -2 times 7, which is -14. And -14 plus 8 is -6. If I was trying to plot these dots, 6, -6 is on my graph. Not bad, right? You did do evaluating absolute value expressions in Algebra 1, correct? Okay, but we don't remember if we graphed them, and probably didn't. Some people might have. Just depends on where you took the course, maybe. All right, let's take it up a notch. Let's add a couple more things. Oh my God, fractions. Yeah, it's okay. You'll be all right. Don't fear the fractions. Fractions are our friends. Yeah, fractions are friends, not food. Let's change colors again because I feel like it and it seems fun. Okay, Daniel Q, quoting you. Fractions are friends, not food. You're very welcome. You're going to be internet famous, you know that? Description, the link to the merch store in the description down below. Absolute value, 3 times, -6, plus 8. Toss in a 4 this time. Like I said, you're going to treat them like parentheses, meaning clean up whatever's on the inside first. -1/2, hanging around outside, on the inside. Well, 3 times 4 is 12, and 12 minus 6 is 6. For those of you that think that you don't know how to, cannot multiply by a fraction without a calculator, you are wrong. I'm going to tell you how, just in case you were never taught how. In mathematics, we can replace the word times with of. They mean the same thing. So instead of saying 1/2 times 6, we can just say 1/2 of 6, which is 3. Oh, but it's negative. So it's -3. There. If I was just guessing and had no idea how to graph, I could at least plug that number in and I could plot the coordinate 4, 5. And the last one, eek, more fractions. So scary. I got to find a new color combination. Once again, that -2 can't distribute to the inside of the bars. The bars are like jail bars. It's not getting in. Mr. M, I definitely can't do that one without a calculator. Yeah, you can. And we will. You know when you say 3/4, it's like saying 3 of these 1/4. 3 of them. So you can actually say, what is 1/4 of 12? And you guys would all say? 1/4 of 12 is... Stop it. 3. 1/4 of 12 is 3. If you're not sure, it's half of a half. Anyway, 1/4 of 12 is 3. So 3 of those 3s get you 9. One minus 9 is -8. My green pen's about to bite the dust. I'm running out of ink here. That gets me negative 2 times positive 8 minus 14. Negative 2 times 8 is negative 16. 16 and 14 get you 30, but they're both negative. And there it is. Now you guys are lucky that you are the last time in the day that I have Algebra 2 honors. Because earlier today, this box was woefully lacking. The first 2 times I taught the material today, I had to keep adding stuff into this box and we had to squeeze things in and it just didn't work out well. So during my planning period, I went ahead and made the notes better and printed fresh ones just for you guys. So if my period 1 or period 3 people are watching the video being jealous, well, they should be, because their notes were not as good as yours. What are you going to do, right? You know what's crazy, though? They get to see all the things that I didn't do right in the notes, and they get to hear all the mistakes and all that, because I always record the last time I do it. That way it's the best performance of them all. So the way I see it is you guys get the best education of all 3 times that I have this class. So how is it that you guys scored the lowest on the test? I'm just asking. I'm just asking. There's nothing wrong with a little bit of friendly competition, right?
I heard first period did really bad there.
First period did the best at a 71 average. Yeah, sad. This class got almost a 67 average. Yes. Yes. Anyway, the beatings will continue until morale improves. So anyway, in this box, we are going to discuss the absolute value function. And I'm going to go ahead and artificially divide the box. Artificially divide. On the left of the divide, we have the parent absolute value function. F of x equals absolute value of x. Mr. M, what's a parent function? I don't remember from Algebra 1. A parent function is what the graph would look like if there were no transformations done to it. It's just y equals the absolute value of x. Y equals the absolute value of x. This is what it's shaped like. And its vertex sits at the coordinates 0, 0. So what I just drew right there is tiny x, y axis. Okay? 0, 0. A little bit of review for us. This graph, this function, is symmetric around the y-axis. That makes it an even function. So just throwing out the review. But because it is an even function, it actually has an axis of symmetry. The axis of symmetry, so I don't have the word of symmetry, but I mean we could sneak it in there. The axis of symmetry is the vertical line that goes through the vertex, which for the parent function happens to be the y-axis. The equation for that is x equals 0. It's not an accident that the vertex is at 0, 0, and the axis of symmetry is at x equals 0, because the axis of symmetry is going to go through the vertex. The axis of symmetry will always be vertical. So it will always be x equals, and then whatever the x value of the vertex is. Whatever that number is, x equals that number is your axis of symmetry. Domain. Domain is what numbers am I allowed to plug in? Well, you can find the absolute value of anything. So our domain is all real numbers. Negative infinity to positive infinity. But the range is the y values that this graph would cover up. I'm hoping you can see with my cheesy little xy axis that I drew that this thing never dips below the x-axis. That means the range is all the numbers beginning at 0 and going up. Side note, it's been brought to my attention that some of my students might not know what the arrows on the ends of those lines represent. I'm being serious. That means this graph never stops. So even though my page comes to an end, the graph doesn't, and it goes forever to the left. So domain goes to negative infinity that way, and the graph goes forever to the right. Domain goes to positive infinity that way. But it also goes up on both ends, which is why both of these y's head towards infinity. A closed dot is an endpoint, and an open dot is almost an endpoint, but it doesn't exist. I guess I got to get this stupid phone call. Now that I'm no longer being interrupted by a phone call. This graph, I want to talk about increasing, decreasing of the parent function. Remember, increasing means if you were riding this thing as a roller coaster, left to right, increasing means you're going up. Well, we're going to pretend that there's not death right there on this roller coaster, okay? But anyway, decreasing means the roller coaster will be falling down. So if we start right here, left to right, we let our roller coaster go, whee! And we didn't crash. We're just going to pretend that there was safety down there, okay? But the point is, this side of the graph is decreasing. This side of the graph is increasing. And when we do increasing, decreasing, we use the x values to describe that. I'll switch up colors because why not? We're going to increase to the right of 0. But remember, for increasing, decreasing zones where they change, we have to use a bracket. So we increase on the right side from 0 to infinity. We decrease on the left side from negative infinity to 0. And there's the bracket. So that is the parent function. That's what it would look like. And if you understand transformations, which is why we spent 3 days practicing them, reviewing them actually, then putting numbers all over the equation really shouldn't frighten you at all. Not one little bit. First, horizontal, inside, opposite. Inside changes do the opposite of what they look like. So this has been shifted, the way this is written, to the right, some value. How far was it shifted? H, to the right. Vertical, outside, same. This has been shifted up. How far up? According to the letter, because it says plus. K. That means the vertex from standard form of an absolute value is the letters H, comma, K. Let me go back to the same colors. H, comma, K. That's going to be here or here. Regardless of whether or not it points up or points down, the axis of symmetry is still going to go right through the vertex, and we'll still have the same x value as the vertex. So the axis of symmetry is x equals whatever h is. Please, you have to say x equals if I ask you what the equation of an axis of symmetry is. If you don't give me x equals and I say, hey, what's the axis of symmetry? And you go 5. Okay, no, what you gave me was a number. You did not give me a line. A line requires x or y equals, and if it's vertical, it's x equals. And the domain, well, look, both these things are still pointing forever left and right. So the domain has not changed. It is all real numbers, negative infinity to positive infinity. Words that I like to use. I ask my students how to find the vertex of this thing, and the answer is whatever makes the inside equal 0, because if you plugged in h, you get h minus h, which is 0. Whatever makes the inside equal 0, comma, the number to the far right. That's what I say. And I'm going to use those words in chapter 2 when we graph quadratics, in chapter 3 when we graph polynomials, some of them, cubics mostly. I'm going to use those words in chapter 4 when we do exponentials, and then when we do logarithms, I'm going to use those words if we ever get to graphing trigonometry. And the reason why I could keep using the exact same statements is because transformations do the exact same thing to every function type. So when you say what makes the inside equal 0, that's you literally saying if I didn't shift, because it's always the opposite. And comma, what's the number to the far right? Because outside same. Okay. Now let's talk about the fact that this points up and this points down. You guys have knowledge of transformations. Which of those transformations, A, B, H, or K, do you think determines up and down? Parker? K. Well, K is an up and down thing, but it determines how far up and down it moved. So while K is a vertical change, it's going to shift it up and down, not turn it upside down. So if it's not this vertical one, then what one is it? You guys get to shout it out. At this point, it has to be A. What's the A value here? It's 1, which is a positive number. So it points up. You could, I know it's not a smile, but you could think of it as positive people smile. So as long as your A value is positive, your graph points up. But if your A value is negative, your graph points down like a sad teacher. Not a single chuckle. Okay. Just have to take the show on the road, I guess. Well, anyway, positive things point up, negative things point down. They have separate domain, or they have separate range, increasing, decreasing information. So artificially dividing. For this image, the range goes up. Up from where? The vertex. And the range is the only time we ever talk about the y values. So this one goes from K up. Whereas this one points down, so K is the top of its range. Remember, you can never put a bracket on an infinity. This one, just like the parent function, is decreasing to the left of the vertex, increasing to the right of the vertex. This time the vertex's x value, though, is h, not 0. So to the left, we're decreasing. So from negative infinity up to h, and the other side of the domain is where we increase from h to positive infinity. But for this one, it's upside down. It actually increases to the left of the vertex, which is nice because now I can write these things in what feels like the correct order. So you say from negative infinity up to h, I'm increasing, and then I'm decreasing after h. Look at all these letters. Do I expect you to memorize all these letters? No, I don't. What I expect you to do is know how transformations affect everything. I expect you to understand the structures. If it's positive on the front, up. If it's negative on the front, down. And I expect you to understand, because of transformations, what makes the inside equal 0, comma, the number to the far right. Because if you can find the vertex and know if it points up or down, that's more than half the battle on a multiple choice test question. You already know more than likely which one of two it is. And you only need a little bit more information to get it right after that. All you'd have to do is plug an x in to get a corresponding y and see which graph matches at that point. You've got the direction, you've got the vertex, you find one more point, you're set. That's it. So no, please do not spend time memorizing this junk. Understand it instead. It's better. So let's graph one. First things first, decide. Does it point up or down? This one right here, class, up or down? Down. Some of you answered. I sure hope that the rest of you just didn't feel like talking. We know it looks like this. Okay? Now what we need to do is figure out where the vertex is. What makes the inside equal 0, comma, the number to the far right? What makes the inside equal 0? Shout it out, guys. Lots of you. -1. One person got louder. Everybody else, except for one other person, stayed quiet. That's scary. Does that mean that you guys really don't know what makes x plus 1 equal 0? It frightens me. I sure hope you do. Could be a long year. And the number to the far right is just 8. Our vertex is at -1, comma 8. Watch out, my grid counts by 2's, but each one of them is, it does go by 1's, but I've only numbered the 2's. So -1, comma 8, and I know that it points down. We're almost there. What I'm going to do is I'm going to throw an axis of symmetry on here. And now I'll just grab another x and plug it in to get one more dot. The strong suggestion is that you stick close to the axis of symmetry. So whatever x you're going to plug in, make sure it's close to x equals -1. What would be a really easy number to plug in? -2 is really easy, and what's the other one that's really easy? 0. I'm going to be real with you. I typically just move to the right, just because. There's nothing wrong with -2. I just really don't want to have to think about what's -2 plus 1. I'd rather just say what's 0 plus 1. Just seems to be easier. So I usually go to the right, and I try to stay close. So I'm going to go 1 to the right this time, because there's no danger of decimals. If there was danger of decimals, I would want to be a little bit choosy. We'll talk about that in a minute. For now, I'm just going to plug in x equals 0. So let's do f of 0. Well, that's just -2 times the absolute value of 1. The absolute value of 1 is 1. So that says -2 plus 8. 6. Once again, substituting a value in for x results in a y. You now have an x comma y that is on your graph. So plot it. It's right here. Nobody corrected me. Did you guys not catch that I put that dot at 0,9 instead of 0,8? Oops. Anyway, vertex -1,8, point at 0,6. If there is a blue dot 1 to the right of the axis of symmetry, there is a blue dot 1 to the left of the axis of symmetry, and you just connect your dots, and you're finished. Can you do that? Can you decide up, down? Can you find vertex? Can you plug an x in? And then just reflect. If you can do those things, you can graph any absolute value graph. But that doesn't mean that's how I do it. Because I've graphed, I don't know, a bazillion of these things, have accidentally learned patterns and tricks. Now, I'm not the kind of teacher that will just teach tricks and patterns without showing you why they work. I use no tricks, no patterns. I showed you exactly how you could do this when you have no clue what to do. However, I'd like you to take a peekaboo at, you already knew it pointed down, okay? I'd like you to take a peekaboo at this line and this line. And tell me what the slope is. What's the slope on the left? What is it? Rise over run. Daniel.
-2. Yeah, -2.
How'd you get for this one?
Yeah, it doesn't go down to the left one.
Well, down to and left one, those are both negative numbers, aren't they? So down to left one, that's -2 over -1, which is +2. Or you could have started right here and said up to right one. Either way, the slope on this side is 2, and the slope on this side is -2, down to right one. See, I already knew that the graph pointed down, and I knew that those two lines were going to have slopes of 2s. How did I know that? You see it, right? From the number in front. The negative told me it pointed down, and then this told me the slope of the lines. I already knew it pointed down. So I just would have gone down to right one, down to left one, and been finished. It's pretty easy to pull off. Someone in first period was like, so it'll always work like that? And I was like, well, let's be really careful about this world. Really, again, it's the same guy too. Man. Completely ruined my train of thought. I don't even know where I was. Okay, so this is a shortcut. I don't want you using it unless you know how it works and why it works. It works because of transformations. Because this line on this side y equals x. This has a slope of 1. This line on this side is y equals negative x, slope of negative 1. This is a vertical stretch, factor 2, which changed my stretch, changed my y values. So my rise overrun, the rise got doubled. It works because of transformations. You're like, whatever, I got this. I'm always going to do it that way. Oh, yeah? Now what's up? Okay. So let's not do this by shortcuts. Instead, let's do this the way that I trained you, and then afterwards we'll see how the shortcut works for this one. First, class, lots of people, point up or down? It's going to point up. Fantastic. Points up. We know that because the 1/2 on the front is positive. So we got an upwards facing graph. And I told you the vertex is going to be found by what makes the inside equal 0. Notice that I was very careful not to say, just switch the sign of what you see in here. It's what makes the inside equal 0. So we're going to figure out what that is. This says 3x plus 6. Okay. Yes? Not 2. Not 2. Negative 2. And here's why. Subtract 6 from both sides. Oh, I see what you're saying. I wrote this wrong. I got you. Okay, you were right based on what was on the paper, because it should have said 3x minus 6 equals 0. And we'll just pretend that didn't happen and make it 3x equals positive 6. And yes, Ilya, x equals positive 2. I am so sorry. I wrote it wrong. I blame the guy that called me twice. So the vertex is what makes the inside equal 0, comma, the number to the far right. There it is. We have a vertex at 2, negative 7. I'm not going to plot this one wrong this time. And I know it points up. I've got an axis of symmetry here at x equals 2. Now, normally, you just grab an x value that is close to the axis of symmetry. I like to go to the right. And if you are not afraid of plotting decimals, then by all means, use x equals 3 because it's 1 to the right. But I'm not going to. I don't want to plot a decimal. I'm going to go 2 to the right. I wonder why I would need to go 2 to the right instead of 1 to the right, thinking transformations. Because this wants it to have a slope of 1 over 2. That's up 1, right 2. It wants it to have that slope. That doesn't mean that's it. But this vertical shrink of factor 1/2 wants this thing to have a slope of 1 over 2. So I'm going to go over 2 to get to the next x value that I'm going to plug in. So I'm going to use x equals 4. And guaranteed, if you pay attention to that denominator and go that far away from your axis of symmetry, you will never have to graph a decimal. What did I say I was using? 4, because that's 2 to the right? Okay, like that. This gives me 12 minus 6 in here. And that's where I could say, what's half of 6? And you would all shout 3. Well, a couple of you shouted. And 3 minus 7 is negative 4. So the coordinate that we're going to find on our graph is 4, negative 4. We put a dot there. If there's a dot 2 to the right of that red line, there's a dot 2 to the left of that red line. And you connect those dots. Now, let's figure out what those slopes were. Remember, it's rise over run. Who could tell me what is the slope on the right side? Just count. Come on, guys. 3 over 2. The slope of this line is 3 over 2. The slope of this line is negative 3 over 2. The point is, why was it 3 over 2? Because that's what you get when you multiply 3 to 1/2. You get 3 over 2. So the trick was still working, and it was working here. The difference was the number in front of this x was a 1, and 1 times 2 is still 2. And the denominator of this 2 was a 1, and that's why I was able to go over by 1. These are just tricks. If you don't understand them and you're afraid you're going to goof them up, by all means, please just plug in an x and reflect it, okay? Here we have an equation. We could see it points up. Because it points up, I automatically know the front thing's a positive number. We already know that. I have a picture. I could see my vertex. My vertex is at 2, negative 4. Well, remember what the vertex does. It's what makes the inside equal 0, comma the number to the far right. Or you could even say this vertex has been shifted right 2, down 4, if you wanted to talk transformations. Right 2, down 4. Oh, here's what I know so far. I know I have a positive a value on the front. I don't know what it is yet. But in my absolute value bars, shift right 2. Remember, horizontal inside opposite. Vertical outside same, down 4. We know that so far. No tricks, methods. How could I solve for A that doesn't involve some trickery of slope? Ilya, got an idea for me?
So you can't just do rise 1 over 3.
Well, the slope trick will work for us, but again, I'm more interested in why this trick is working. So yes, that will get you the right answer, but I want to know, what if you forget that? How could we just use our graph because you forgot the trick come test time? What other information does this graph give us that we haven't mentioned yet? That's what Ilya said. We don't want to use the slope thing because that's, like I said, that's trickery. Now in a minute when we get A, we're going to confirm that it's the right slope. But I want to ask you how we could solve for it if you forgot the trick. Come on. Someone in 4th period said it fast. Sophia, give me a try. Worst case scenario is you're wrong and it's no big deal. What would you like to substitute? So there it is. Sophia says, what if we just substituted one of the coordinates in on the graph? Exactly what we would do. Notice that this thing has x's and y's. All we have to do is go pick a random xy that this thing goes through, pick one of the pretty ones, and by pretty I mean goes through a pretty coordinate grid crossing, like right there, at 5, negative 3. And you're going to substitute the value for x and the value for y into this equation. Our y value is negative 3. We'll be solving for a. The x value was 5. And now we just do the same stuff that we did at the very beginning of the lesson. Evaluate. Well, 5 minus 2 is 3. And the absolute value of 3 is 3. Add 4. And divide by 3. And then, yes, if you count up 1, right 3, you will find the coordinate 5, negative 3. So we know that the slope trick works. Again, it's a trick. I'm not a fan of just teaching the tricks. I want you to know why it works. So if and when you forget the trick, because let's be real, in a month, are you going to remember that? Probably not. But if you know that every pretty grid point is an x, y, you could always plug them in. Boom. There it is. And the rest of the lesson is just reviewing transformations because I think they're that important. Before we get to the transformational review, do you have any questions about graphing or getting the equation of the graph that I could address? No? I feel like there should be more questions in this class period than my others. Okay. Then how about this? What transformations have to be done to the parent function, absolute value of x, to get this function? It's 3 transformations. Who can give me the first one? Brody? Awesome. Vertical shrink, factor 1/3, because vertical outside same. Outside change is going to be following PEMDAS. For the next one, there's two different options. It doesn't matter which one you say. Daniel Q?
Horizontal shift to the right 2.
Shift right 2 units? I agree. Yeah?
Shift down 4 units.
Shift down 4. Perfect. Awesome. Okay, now let's check this out. I had somebody ask me a question during the test, which tells me that I needed to review the concept. Do you have to say vertical shrink factor 1/3 as the first transformation? No. What else could have been the first transformation that you mentioned? Can I get somebody new? I mean, I appreciate you 3 or 4 that have been talking to me all day. Okay, Megan? I could have said shift right 2 first. It didn't matter actually when I said shift right 2. Could have been first, could have been second, could have been third. The only thing that mattered in your ordering was that the vertical shrink was mentioned before the shift down because of PEMDAS. But because horizontal changes and vertical changes don't affect one another, when this one gets mentioned doesn't matter. And I had somebody pick a wrong answer choice on the transformations question because they thought it had to be in a specific place. No, no, no. This one could have been first, it could have been second, it could have been third. All that matters is that this was mentioned before this. That's all that matters. Okay. And the last one, again, transformational review says f of x is the original, g of x is the new one. How do I turn f of x into g of x? In description. Can someone tell me in words what to do to f of x? Shift left 3. And is there someone then that would be brave enough to write me the rule that says shift left 3 units, the function notation rule? I'm trying to get new people. Barry? The f of x plus 3 in parentheses is exactly what it would be. Awesome. All right. Thank you so much, nerds. I appreciate all the effort.